Hi everyone, I'm Sophia and this is my week 8 reading. So in week 8 we talked about circuits and in a circuit there's always a non-zero electric field acting on that circuit. So it emanates from the positive terminal of the battery and points towards the negative terminal of the battery. And this electric field always keeps the electrons flowing around the circuit and the wires. So basically, the circuit never reaches equilibrium where the conductor becomes polarized and the net electric field inside the circuit is zero. Okay, and another thing we discussed was the node rule. So it's basically saying that the change in electric potential as you go all the way around the circuit in a round trip is zero. And we want the wires and other connecting elements that in the circuit to influence the electrical potential as little as possible. So the change in electrical potential across the wires will be nearly zero. And the change in potential across batteries and other important elements like light bulbs will be non-zero. But since the total round trip change in potential around the circuit must equal to zero, then the change in potential across the battery and across the light bulb must be equal and opposite so they cancel each other out. So another thing we talked about was resistance. So resistance is the magnitude of the potential difference divided by the conventional current. And this is basically Ohm's law. And this serves as a way to compare, the difference across, the difference in electrical potential across various elements in a circuit. Then we talked about resistance in series and in parallel. So if you have two resistors in a series, then you can add the changes in electric potential across both resistors. And you can also add the resistance of the two resistors together. So if you want to simplify these two resistors into one resistor that will have like an equivalent resistance equal to the resistance of the two of these resistors, then you can just add up the resistances of each of the resistors in the series to get the equivalent resistance, and that's because both of the resistors have the same current flowing over them. And in parallel, the current actually splits between the two branches of the circuit. So the change in potential across the two branches is the same, and the equivalent resistance is going to be the sum of the inverses of the resistance of each individual resistor. And finally, we also talked about capacitance. So capacitors are basically two oppositely charged plates separated by some distance. And the two plates produce a constant electric field. And the electric fields from these two plates point in the same direction, away from the positive plate and towards the negative plate. So you can multiply the electric field by the separation distance. You can multiply the net electric field by the separation distance between the plates to get the change in electrical potential across the capacitor. And capacitors basically act to store charge. And capacitance is how much charge we can store per unit of potential difference. And so I think the most confusing thing about this material was how abstract it is. And, I'm still looking through resources to kind of help me understand this, but the student wikis and CampusWire are pretty helpful. And in my previous classes, I started studying resistors in series and in parallels, so equivalent resistance is kind of similar to me, but then we didn't really talk a lot about capacitors and circuits that contain both capacitors and resistors. So there was definitely a lot of new material this week too. And in my field of study, I don't really deal with a lot of this. So I'm a biomedical engineering major focusing on immunoregenerative medicine and stem cell therapies. So this is not exactly up my alley, but in some of my classes where I have to build medical devices, we would use the principles of current and such. But yeah, thank you.